Castings, a vital necessity in all engineering industries. Some simple, others more complex. Many of them are hollow, like this typical pipe T-piece. How are such castings made? From the original machine drawing of the required part, a wooden pattern is developed. Frequently it's designed in two pieces to assist the moulding processes. Dowels in one part and sockets in the other ensure perfect registration when the two pieces are put together. Once it has been designed and made, a pattern may be used many times. Here we see a hand moulder putting down the bottom half of the pattern onto the wooden board that will form a temporary support when the mould box is filled with special moulding sand that is carefully rammed home around the pattern. The success of hand moulding is entirely dependent upon the skill of the moulder, whose knowledge and judgment determine how tightly the sand should be rammed up. After removal of surplus sand and squaring off the face of the lower part of the mould, the second part of the pattern is fitted on. Dry parting sand on the mould face ensures clean separation of the two halves of the mould later. The two mould boxes are kept in correct alignment by register pins. After separation, the patterns are withdrawn from the two half moulds. The bottom half of the mould is called the drag, the top half the cope. The pattern is first wrapped to clear it and give an easy withdrawal. For a hollow casting, a core of baked sand is used to prevent the molten metal from filling the whole space left by the pattern in the mould. Here you can clearly see where the metal will flow to form the walls of the casting. The register pins make it possible to replace the top part of the mould in its correct alignment. The moulder also controls the pouring of the metal. Later, he breaks down the mould. The core sand is broken out from inside the hollow casting, which is then fettled and machined, and we have the finished job. The design and construction of a pattern will vary with the complexity of the casting and the number required. For simple shapes, a complete solid pattern may be used. But usually, the two halves of the mould are formed from two half patterns. If a casting includes an overhanging shape that would prevent the whole pattern being withdrawn straight from the sand, this overhang may be provided for by means of a loose piece which remains behind in the mould and is subsequently drawn out sideways. Keyways or pegs hold the loose piece on the main pattern. All these technical points are borne in mind in deciding the form the pattern shall take. Then what is known as a drawing board is prepared. It is made to the dimensions of the finished casting, but a scale is used that automatically allows for shrinkage of the metal during casting. Allowances are added where parts are to be machined, and adjustments may be made to ensure a sound casting. The position and dimensions of the prints are shown. These will form recesses to support the cores in the mould. The drawing on the board is then varnished to preserve its main features. Most patterns are made of wood. The pattern maker first calculates the quantity he will want for the whole job, probably choosing yellow pine for most work, mahogany for special patterns, or to reinforce the softer wood. The raw planks are skimmed and put aside in the shop to warp and settle. They are then thicknessed and are ready for use. For hollow castings, cores will be required, and the pattern maker will usually prepare first the boxes in which these cores will be moulded. Most cores are made in two halves that are gummed together after being hardened in an oven. The sections of the core box are built up to stepped channels ready to be given final shape on a wood milling machine. Special contours are indicated by lines drawn on the ends of the channels. In the absence of special indications, it is always understood that the channels are to be semicircular. Returning to the main pattern. This is first built up roughly from squared sections of wood. In assembling several thicknesses, they are arranged so that if the grain shrinks, they will tend to pull apart in the center and not at the ends. This gives the most stable construction. The various contours are then indicated on the rough carcass. Shaping is done with the aid of machinery and with the hand tools of the craftsman. Templates are used to control the progress of the work. Some shapes are prepared on the sanding wheel. The various parts are assembled by gluing and screwing, a method of unit construction that will help if repair or modification is called for later. An important component is the metal wrapping plate that will assist the moulder in obtaining clean withdrawal of the pattern from the mould. Small patterns are generally solid, but large ones are made hollow to keep the weight down. Some half patterns have removable pieces that can be changed over so that the two halves of a non-symmetrical mould can be made with the one pattern. Proper taper, smooth contours and a good clean surface finish are essential if the pattern is to work well and give good shapes. All screw holes are plugged and sanded before painting. The painter mixes his own shellac paint, knowing that the success of the job will largely depend on its quality and consistency. A scheme of contrasting colors is used to assist the moulders. Machining surfaces are painted yellow. Brick red and black are used to distinguish the core prints from the main pattern. Core boxes are painted in the same color as the main pattern. The spirit color dries very quickly and is followed by a rub down and spirit varnishing. The fine finish of the patterns is evidence of the craftsmanship that has gone to their design and construction. Whether they are intended for the hand moulder or for quantity production, the patterns have been designed to give first-class results with the greatest economy of labor in the foundry. When cores are required, they must be prepared before the moulder can do his work. They are made in a separate workshop from a mixture of old and new sand with the addition of oil and cereal binders to give added strength. Here again we see the part a core plays in making a hollow casting. Here is a similar core being made. The shapes are formed by ramming the sand into wooden molds known as core boxes. Most cores are reinforced, the simpler ones with cast metal bars. More elaborate ones with cast grids. When the molten metal reaches the cores, gases will be driven off. To allow them to escape, the simpler cores are pierced by vent wires. In other cases, hemp is placed in the core box and withdrawn when the core has been formed. Where the venting device cannot be withdrawn in this way, wax venting is used, which melts when the cores are baked, leaving a free passage for the gases. Baking in a closely controlled temperature for the correct period firms and hardens the core. Some cores are vented after baking by cutting a channel in the surfaces. Half cores are now gummed and joined together. The last operation is to apply graphite paint that will avoid fusion of the core sand with the metal of the casting. So far we have seen only hand moulding, generally used for small quantities or more complicated castings. The proper handling of the mould and of the pattern, and the correct disposition of the various cores, requires a high standard of skill and craftsmanship, but the rate of output is low. Wherever possible, speed of output is achieved by the use of machines which fill the mould and pack the sand by jolting or squeezing, or a combination of both. Sand is automatically conveyed to the job, and the maximum output is obtained without undue burden on the workers. Patterns for machine moulding of a wide variety of parts are usually of wood. Dowel pins locate the patterns in the machine so that both halves of a mould can be made separately and match perfectly. There is almost no limit to the variety of patterns that can be used, and the machine can be employed for one-off jobs as well as for large quantities. For large-scale production of small simple castings, a metal plate mould is used, the two halves of the patterns being on opposite sides of the plate. This type of pattern is used in the squeeze machine, which is hydraulically driven and turns out a boxless mould. The lower part of the machine acts as the drag. This is filled with sand and the pattern plate swung into position. The upper part of the machine is then lowered to form the cope, and hydraulic pressure squeezes the two parts into a mould. The pattern is then withdrawn and the two halves of the mould brought together and placed on a conveyor belt to be carried to the pouring station. Larger work is done on the jolt rollover machine. When the jolt principle is used, each half of the mould must be made separately, so that the sand is driven towards and not away from the pattern in each half of the mould. The mould boxes are built up to the desired depth with unit sections, and the box and pattern are located accurately on the bed plate of the machine by dowels. The machine incorporates mechanism for rolling over the heavy mould and transferring it to a conveyor line. The other part of the mould is then prepared on the machine and lowered into position at the pouring station. In the jolt and squeeze machine, the mould is first bumped up and down to firm the sand. It is then consolidated by hydraulic pressure. Again, each half of the mould is made separately, register pins ensuring exact matching when the two halves are brought together. Filling and consolidating the sand in very large moulds is nowadays done with the aid of the sand slinger. Sand, from which all foreign bodies have been removed, is applied to the mould box at high velocity. details of the mold are finished by hand ramming. The pneumatic rammer is also used as a time and labor saver. The mold having been prepared by one of the above methods, it is carefully finished and is then ready for pouring. The molten metal, at precisely the right temperature for the work being done, is now poured into the mold. Let us, with the aid of a model, see what happens inside the mold. A gate or downpipe is provided through which the metal flows into the mold. In most cases there are also risers which permit the escape of the gases and allow slag and other foreign matter to float clear of the casting. When the metal has set, the mold is knocked out and the rough casting is allowed to cool before undergoing further operations. Rapid mold preparation, such as we have seen on the squeeze machines, calls for equally rapid methods of pouring. The automatic conveyor takes a constant stream of newly made boxless molds to a point where they are weighted. They then pass on to the pouring station. Here, operatives, kept fully supplied with molten metal, travel along with the molds, pouring as they go. By the time castings have set, the molds have reached a point where the weights are removed from them. They then pass on through a tunnel to where the molds are broken down. Inside the machine, the assemblies are tumbled, the sand going below for recovery, and the castings emerging on an elevator and passing outside the factory bay for conveyance to the Fettling shop. Other types of casting are tumbled and sandblasted to clean them after they reach the Fettling shop. For big and heavy work, the hydroblast method of cleaning is employed, using a jet of water and sand at a pressure of 600 pounds per square inch. All castings are fettled to remove excess metal. These castings are the finished product of the foundry and raw material for the machine shop. Accuracy in pattern making, molding and casting reduce to a minimum the amount of machining necessary to produce the final engineering product.